Good afternoon. I'm Frederick Fowles, Creature Department Head at Rainmaker Entertainment. So, Rainmaker Entertainment is a multifaceted animation studio that innovatively creates and produces compelling characters and timeless stories for a global audience. Our range covers feature films, DVDs, and short films and shorts. So in production at the moment, we have Escape from Planet Earth, and we have a short trailer, and there's some other work as well that we've done, some of the short films and direct-to-DVD as well.
Look, the way I see it, you have two options. One, let me out of this glass jar. Or two, I'll take that as a two.
So that was just some of the work the artists have created at Rainmaker. We're going to now focus on the Creature Department. And the Creature Department services the needs of production for rigging, facial setup, and simulation as well. We also run the simulation shots as well in-house. But today we're going to focus on rigging at Rainmaker. And we're going to discuss two distinct approaches we take at Rainmaker. One of these is rigging using the API to develop custom nodes that support the needs of the rigs for production. The second approach that we're going to look at is our facial system, which is called Twitch. And Twitch utilizes Maya's built-in systems to produce a facial animation system that meets the needs of the artists and production alike. So there's some obvious requirements we need to take into account when we're rigging. So we decided to focus our development on a build-rebuild system. So some of the technical production requirements we established for the system were to accommodate design changes late in production, non-destructive rig development in animation, be able to address technical, Rainmaker's own established pipeline requirements as well, be able to address technical issues not considered during pre-production, and most importantly, artistic iteration. It's a visual medium after all, and one thing we need to do is be able to iterate on the asset and actually give the artist the time to create the quality they want from there. So our approach to do this was to actually create a studio mesh and make a consistent mesh that we could build our rigs from. So the mesh is really a data asset, and during production, it serves as a reference point for pipeline and for the artists alike. All the characters are built from this, and all the rigs are derived from this asset. And for Escape, we have two distinct types. Those are aliens and humans. So what we decided to do is create a unique studio mesh for each type on the film. So we have a mesh for the humans and the aliens alike. And both of these are created from their own unique studio mesh. And the rigs are derived from their unique data asset, derived off this mesh. So now we can see the process in Maya, and every rig can be derived off a mesh that can be created to any character. So for the studio mesh, you can create any character, no matter how different from the original. And for Escape, it was similar for the humans as well. We could create any of the characters from the same studio mesh, their own character-specific mesh. And this is also true for the aliens as well, though it was a actually different mesh that we used. Just because the characteristics were so different between the two, we needed to define them differently. So now we have this mesh, and we can drive our rig off this mesh. So how are we going to do this? So what we decided to do is be able to use a system where we could select 3 points on the mesh, and then from that we could create a barycentric coordinate system which we could offset any rig components or any joint and build a skeleton off that. So we could blend shape this mesh into any other character, and the positional points would be relative. So we did this by designing our own custom node, which we wrote in Maya's API. So now we can see that process in Maya. And we have a video next, which is presented by Ron Bublitz, and he was one of the developers on the system, and it's narrated by him.
I'd like to present our skeleton construction tool called Marrow and a custom plugin called BerryJoint. There were several issues that we wanted to solve when designing this tool. When the modeling changes happen, we wanted the joint positions to be easily and automatically updated. And also when those positions are moved, the orientation relationships to also adjust automatically. So when we define these behaviors, we could then extend these across multiple characters as long as the mesh topology was the same. So for example, this mesh could be morphed into this character. And our ultimate goal was just to rig this character once, and when the mesh is morphed, that the rig adjusted along with it. So we basically took Maya's joint functionality, disassembled it into its multiple parts, and then recombined these parts into the exact behavior we desired. We did this by creating a Python plugin called BerryJoint, which consists of a custom locator, an IK solver, and 2 manipulators. So the first step is to specify the BerryJoint position. The main issue when locating joints is that you're dealing with world space coordinates. The mesh that you're rigging really has no relationship with the joints. But if we could specify 3 known points on a mesh, we could determine a new coordinate system. So here we're going to zoom into the shoulder area and choose 3 points. So 1, 2, and 3. So now that we've created this joint, what this has done is taken those 3 points and made a barycentric coordinate system out of it. And the joint is located between the first and the second point. And we're able to take a manipulator and move it into the exact location that we want. So now as we morph this character, you notice that the joint is moving relative to the way the mesh is being updated. So let's create 2 more joints. So first one is an arm joint, and choosing 3 more points on this mesh. And we'll go and create a forearm joint. So 1, 2, and 3. So once we have the positions located, we can now describe the orientation relationships between these various joints. And there are several different options we can use. By default, you notice that the shoulder joint here, the z-axis is pointing to the 3rd point. And our standard is to have the x-axis point to the next joint in the chain, so you usually want to change this. And this can be easily done. We'll just go to the arm joint, set it to be current, and set it to be the child orientation. So you notice that the x-axis is now pointing towards this next joint. Sometimes the z-axis isn't pointing in quite the correct place, so what we're able to do is create an orient target, which is basically a locator. And we can attach it, and let's just move it into the correct position here. And you'll notice that the z-axis is now pointing towards that orient target. And the good thing about it is it's also part of that same barycentric coordinate system, so that anytime the mesh morphs, it will also go along for the ride. So another option we can have here is to set a joint as the orient parent. So we'll do that for this forearm joint. And you notice that it now has the same orientation as the arm joint. Finally, we can set a system, a plane with these 3 joints and have the z-axis normal to that plane. So we'll do that here for the arm joint. We'll set the shoulder as the orient parent, the forearm as the orient child, and you notice that the z-axis now is normal to that plane. I'll just move that arm around so you can see. So I'll just load another file here. So once we have our skeleton correctly positioned and oriented, we can describe the hierarchy relationships between those joints. And so those are the purple lines. So all we have to do really here is to press the build rig button, and it generates the final skeleton for us. And those joints are properly located and oriented and ready to be bound. And then if we morph that character to the other character and press the build rig button, we get that character skeleton also ready to be bound. And that's it.
So now we have our skeleton and our articulation points derived from the mesh. So we can also, from that, we can create our own IK systems and that will follow through with the orientation of information we've actually stored on the mesh. So from this, we can then procedurally build our characters. So we can actually do this as soon as geometry is published and actually drive a skeleton from that system. And so being, we can then build a procedural rig. We got a video of that next process. I'll take you through that.
Rig Builder. Rig Builder is a procedural creature rig generation system developed in Maya and is used to automate rig creation at Rainmaker Studios. It's written in Python and Qt and with several custom plugins and nodes. Rigs built from the builder share common features, such as base topology, controls, and procedurally generated skeletons. All you need to build the rig with the system are geometry, skeleton, a rig description file, which is a simple Python file, and weights. The geometry shown here is one of our characters from our show. The skeleton was one that was built using the procedural skeleton generation tool shown earlier. The rigger interacts with the builder through the Rig Builder GUI. It is a Qt app which wraps most of the common user features and interactions. The first thing that the rigger must do is set up his environment using the project manager. This allows the tool to define paths and directories to a show or to the current project. Then he just types in the name of the character that he's working on and sets the base type for that character. In this case, our base character will be Squirt Supersuit, and the base type will be the same. Then we decide whether we want to build a debug version or a production version. I'll choose the debug version so we can see the output. Then I press create, and it will clean out the scene. Building the scene imports the skeleton, the geometry, and procedurally generates all of the rig components needed to build the character, and also loads the weights. This should take a few seconds, and there we go. This is a finished character, completely rigged and in debug mode and ready for us to test. What we can do now is, using the builder, we can import some test animation to test the rig. Actually, I will rebuild the rig in production mode so that we can test the animation. This will build it in production mode. And that's a completed production rig and ready for us to test animation on. And there we go. That's a procedurally generated, completed production rig.
So that's what we do for the main character types that we've got on Escape. But what we're going to do for the other characters. So early on, we realized that the need to rebuild wasn't just localized to the main character types we had. So what we're going to do for the different characters that were, some of the main cast. And what we decided to do is exactly the same process. The only difference is we take the character's own geometry mesh and use that as the studio mesh so that we can derive the rig off. So we take it through the exact same process. And what that gives us is any change, whether it be a design change or just any update to the mesh, size, localized change, we can rebuild this asset in the same consistent manner that we do for all the other characters. So what did we achieve with the process? One of the main achievements that we found was that we reduced the workload from design changes in production, and that was huge. So the main features that got us this was that the mesh could be rebuilt from the rig when the character shape is changed. And also we can store orientational and vector information on the studio mesh. And we can use this to rebuild any of the rigs. We can also store data as sub-assets that can be loaded to build the character and define the modules of the rig that we build up, for production. And also, any custom changes, we can publish them when we publish the rig, and they can be loaded up and rebuilt if we need to rebuild the rig at any time. So that's the build-rebuild process that we use for character rigging at Rainmaker. And it uses custom nodes, mostly written with Maya's API. So our next approach is for facial rigging. So this is the second approach that we take for rigging at Rainmaker. And it doesn't use any custom nodes. It uses everything that's out of the box from Maya. And it creates a flexible but feature-rich facial system for animation. The system was developed by Henry Chow, and it's a great example of development from the artist's perspective. We can now demonstrate this on two diverse characters from Escape. So Twitch is built with two systems. There's an articulation layer that uses joints and clusters to deform the mesh. And then there's also a deformation layer, which is blend shapes, which are controlled from poses on the animation panel to define the pose of the face. The system is presented to the animator with an animation panel that they can control, and it gives a huge range and a lot of flexibility from character to character. And one of the things is that we needed to focus on was the eyes, that they needed to be very expressive, and we needed to be able to get the same range from one character to the next. Because the mesh is identical, and we want to be able to produce as quickly as we can different shapes. And present the animator with a consistent system that they can animate with. So this is one of the main characters, Scorch, on Escape. And there's advanced mode to the system as well, where the more senior animators can take the model and take it off design concept a little bit. But there's a huge range within the system. So when we build Twitch, we have a rig build system, and we also have shapes. So the artists create an array of shapes for the characters. And this is an example of a different character from one of our shorts, but it uses exactly the same system as the character from Escape. And the array of facial shapes are identical. It has exactly the same range, but it is a totally different character, and the face is very nondescript, but we can get a huge performance out of that with the system. And we can take a mouth that's really wide, and we can take that down to a very small pose, even maintaining the topology that we need to. So this is from our short Luna, which is presenting in the Electric Theatre this year. And as you can see, it's pretty expressive, and the animators actually love the system. So it was a reason for we chose Maya for the tools that we developed. You know, being able to custom develop rigs and a system that needed no API development but still gave us a huge range of performance was a huge sell for us. So we can. That's all we've got for you today. I'd like to thank Quentin King and Ron Bublitz for the help and development at Rainmaker. If there's any questions, we can take them offline afterwards. Thank you.
Thank you very much, Frederick.